All right, hello. I hope you can hear me. If someone can let me know in the chat if the audio is working, that would be helpful. But welcome to the first of several review sessions that I'm planning to lead in the weeks leading up to the final exam. And these are not going to be quite the traditional review sessions because I'm going to do some review of older material that was covered in the first 3 midterms, but I also want to talk more in depth about the material that we're covering in the last portion of the course, specifically about integration and finding antiderivatives. And so it's kind of like review, but also I'm talking about the material sort of as we're doing it. So I've got a lot of things planned for this session. And starting with going through the activity that we did last Friday in class. It's a really good activity. It ties together a lot of the really important concepts from this portion of the course. And the last thing I wanted to say is that these recordings will be available for the next 7 days, I believe, on Twitch. I might see if I can put them on YouTube also, so that they stick around beyond those 7 days. So if anyone has questions at any point, please just send me a message in the chat. I am more than happy to address any and all questions. You can also send me an email. I will, if you don't have a Twitch account, you don't want to send a message in the chat, I will try to keep an eye on my email also. So, without further ado, let's dive into this activity. So we were imagining a car traveling along a highway, north being the positive direction, south being the negative direction, and the car's velocity is increasing at a constant rate of 2 miles per hour squared. Hung like a polo horse. Yes, I will do my best to try to get it onto YouTube. The only thing is I'm not recording it locally. I think it's possible to transfer the recording from Twitch over to YouTube. Okay, so 2 miles per hour squared. I just want to point out, first of all, that's a really funny value because it's extremely slow. 2 miles per hour squared means you are increasing at a rate, your velocity is increasing at a rate of 2 miles per hour every hour. So if you step on the gas pedal, after 1 hour you will be going at a slow walking speed. It's just, I think someone didn't think about the units when they wrote this activity. So 2 miles per hour squared has a name. This is called the acceleration. This quantity is describing the rate at which the car's velocity is increasing. It's the rate of change of velocity. That's called acceleration. Okay, so they wanted us to sketch a graph of the car's velocity. It's going to look something like this. How do I know that? Well, I know that the velocity is increasing at a constant rate of 2 miles per hour squared. That constant rate of increase of 2 means that this is a straight line with a slope of 2. And they wanted us to pick out a particular value for the y-intercept. So let's say that's -4. -4 meters, miles per hour. Miles per hour. Describe the motion of the car. So we should probably find when this is. Our velocity, because it's increasing at 2 miles per hour, is going to have the form 2t plus a constant, and I've chosen that constant to be -4. So 2t minus 4, if I set that equal to 0, I find that the car's velocity is 0 at time 2. I guess that would be 2 hours. Again, the units are really weird here. We should have done meters per second. That would have made a lot more sense. But to describe what's going on here, the car starts out traveling 4 miles per hour in the south direction. It is slowing down, however, at a constant rate. And after 2 hours of slowing down, it comes to a stop. And then it turns around and starts driving north at a very slow rate, but getting faster over time. We were supposed to find an expression for v of t. I already wrote that down, 2t minus 4. And of course, you were able to choose any value you wanted here. They just suggested that you make it negative. So the relationship between velocity and position, or displacement, which is how the position is changing over time, is that the displacement of the car is represented by the net area, or sometimes we call this the signed area of the region bounded by the graph of the velocity. They're going to ask us about the time, or the region between time 2 and, time 0 and time 5. So I'm going to sketch that in here. And what they mean by the net velocity is that this portion above the graph is going to count positively, and the region below the x-axis is going to count negatively, which makes sense if we're thinking about displacement. During this time, the car is moving backward, or to the south, and during this time, the car is moving north. So as it turns around and goes north, some of that distance it covers just undoes its progress in the south direction. It cancels out. Overall, because this triangle is bigger, you can see it goes farther in the north direction. So it does end up to the north of where it started. A common mistake that I see on this activity is thinking about this area here, but there's really no reason that we would consider this line down here. When we're doing integrals, we're always looking at the area between the curve and the x-axis, not just area below the curve, because you could go down infinitely far. But we're looking at area between the curve and the x-axis. Now we're going to calculate the displacement of the car between time 0 and time 5. We're doing a little bit of geometry here. This triangle has a base of 2 and a height of 4, but it's below the x-axis. That's going to count negatively. So the area of a triangle is 1/2 times the base times the height. But then this part above the x-axis, this has a height of, it has a base of 3. So that's 5 minus 2, and it has a height of 6. And I know that it has a height of 6 because I have an equation for velocity. If I plug in t equals 5, I get 10 minus 4, which is 6. So the area of the purple triangle there is 1/2 times the base of 3 times the height of 6. And this comes out to minus 4 plus 9, which is 5. And I'm going to not forget my units. The units here are miles. So what that's saying is not that the car traveled 5 miles. The car actually traveled 4 plus 9, which is 13 miles, but it traveled 4 miles to the south and then 9 miles to the north, which means it ends up 5 miles to the north of where it started. That is what displacement means. Now, the next part asks us to find the most general antiderivative for v of t. Our velocity function was 2t minus 4. An antiderivative of that would be t squared minus 2t. T squared minus 2t is an antiderivative, but I can add on any constant I want. And that's still an antiderivative, because when I differentiate this, the 17 goes away and I just get 2t minus 4. So to represent the most general antiderivative, we write a plus c, indicating that any constant there would give you an antiderivative. And s of t represents the car's position as a function of time. And this unknown constant represents the fact that we weren't told anything about where the car starts out. We're only told about its velocity over time. If we were given its position at some moment in time, we could solve for this constant. And then we would be able to know where it is at every moment in time. As it is, all we can tell is where it is at every moment in time relative to where it started. So at time 5, I can tell you that it's 5 miles farther north than where it began. Where did the 1/2 come from in the previous part? Oh, it's because the area of a triangle is 1/2 times the base times the height. That's what that was. The 2 and the 3 were the bases of the triangles, the 4 and the 6 were the heights. Great question. Okay, now we're going to use our expression for the position to evaluate s of 5 minus s of 0. And again, s of 5 minus s of 0, the difference in the positions at time 5 and time 0 is telling us how far away the car was at time 5 from where it started out. So I'm going to plug 5 in to this equation, and you might be worried, how are we supposed to get an answer when we have this unknown constant? But it's okay, it doesn't actually matter what that constant is. Because, and it's very important that these parentheses are here, this entire quantity needs to be subtracted. When I distribute the minus sign, that c becomes negative, the constants cancel out. It doesn't matter where all of this is happening. All that matters is how far the car travels. So I get 15. And 15 is not, oh, I forgot to include units, that's 15 miles. 15 is not the same as 5, which means I did something wrong. We are 19 minutes in, and I've made a mistake. That's alright. Okay. If anyone sees my mistake, and you want to leave me a message in chat, that'd be helpful. Oh, I found it. The antiderivative of 2t minus 4 is t squared minus 4t, not t squared minus 2t. That was the issue. And I see that that's going to fix our calculation here, because now this 10 becomes a 20, and 25 minus 20 is in fact 5. So it's easy to miss while you're just working through this activity. It's easy to miss how cool this is, that we did two completely different things, at least ostensibly different things, and we got the same answer. In question 3, we just did some geometry. We subtracted the area of the green triangle from the area of the purple triangle. Just basic geometry. Nothing to do with calculus there. In part 4, we did some calculus. We took the equation of that straight line, and we thought, what's a function whose derivative is 2t minus 4? And then we plugged in 5 and plugged in 0 and subtracted. Completely different thing. Geometry versus doing some calculus, finding an antiderivative. But we got the same answer. And of course, that's not coincidence. This is the fundamental theorem of calculus, part 2. So the theorem style statement that they want us to write here is that the integral from a to b of f of x with respect to x is equal to capital F of b minus capital F of a, where capital F is an antiderivative of little f. The left-hand side here is representing this geometric thing that we did. It's the net area between the curve and the x-axis. I keep saying x-axis. I guess technically I mean t-axis here. And the right-hand side is this totally different thing we did, which is finding an antiderivative, plugging in 5 and plugging in 0, and subtracting. So the fundamental theorem of calculus, part 2, says that these processes, which look completely different, actually always are going to give you the same thing. And of course, there's a hypothesis here. For this to be true, I think you need to assume that little f is continuous. I'm not worrying about the details here. But yeah, in lecture, I don't know if everyone's instructor got to this. In my class, I did have time to do this calculation with a limit of Riemann sums. It's a bit of a pain. It looks kind of like this. We did all this calculation, and we got negative 27/4. It's a lot of calculation, but it's just really involved details for a pretty simple idea, which is we're using rectangles to approximate the area. And we just want to use an arbitrary number of rectangles and then let that number go to infinity. But we can compute this using this fundamental theorem, and it's a lot less work, but of course it is using this theorem, which is a very deep and powerful mathematical idea. And if you wanted to prove that this is true, it would be just as much work as doing the limit of Riemann sums. Okay, so how does this go? Well, the theorem says find an antiderivative of x cubed minus 6x, and an antiderivative is going to be 1/4 x to the 4th minus 3x squared, and we evaluate that from 0 to 3, which means plugging in 3 plugging in 0 and subtracting the results. So this is 81/4 minus 0. Oh, sorry. I plugged in 0 here. I was supposed to plug in 3. I plug in the zeros over here. So 81 fourths minus 27. That's all 0. If I get a common denominator, 27 times 4 is 108. 81 minus 108 is negative 27. So I, once again, get negative 27 fourths. So that is this activity. This is a great activity because it introduces you to the fundamental theorem of calculus, which is it's the biggest theorem in calculus. It's what we've been building up to all semester. But I think it really does a great job of concretely illustrating the two completely different calculations we do, but that give you the same answer. Let me pause for just a moment in case there are questions about this activity. Otherwise, I will move on. Alright, I wanted to next do a couple more examples of integrals. So let me set up a notebook here. Let's compute this integral of a function that's defined piecewise. And if you're watching along, maybe try to work ahead. If you're watching the video rather than watching this live, you could maybe even pause the video and try to work this out yourself. I'm going to do this two different ways. So actually, see if you can do it both ways. I'm going to interpret this geometrically and then also use the fundamental theorem of calculus. So the first thing I think we should do is sketch a graph of this function. If you just wanted to do this algebraically using the fundamental theorem, it would not be necessary to sketch a graph here, but it's one good way to go about this. So the line y equals x plus 1 looks like this. We've got that from -1 to 0. And then from 0 to 2, we have the constant function f of x equals 2. And then from 2 to 3, we have 2 is less than or equal to 3 is less than or equal to 3. I meant to put x there. We have the line y equals 3 minus x, which looks like this. So that's our function. Now, if we're going to integrate this from -1 to 3, that means the area underneath the curve, or the net area between the graph and the x-axis. But this shape happens to be made up of some pretty elementary shapes. It's a big square and two small rectangles. So the area of this rectangle is 1/2 times base times height. The area of this square is the base times height. The base and the height are both 2. And the area of this triangle is again 1/2 base height. The base is 1, the height is 1. So the total area is 1/2 plus 4 plus 1/2, which is 5. So we did have to do some work to sketch the graph, but once we did that, the rest was easy. It's areas of 2 triangles and a square. No more calculus needed. The only real downside of this approach to evaluating integrals, other than the fact that you have to work out what the graph looks like, is that you can only do this with nice functions, which basically means straight lines or maybe semicircles. Shapes that you know geometric formulas for. The other approach would be to use the fundamental theorem of calculus, and because we have 3 different portions of this piecewise function, we need to split the integral up into the 3 different pieces. So we'll integrate from -1 to 0, and then we'll integrate from 0 to 2, and then we'll integrate from 2 to 3. I have 3 integrals now, which seems 3 times as bad, but actually each of them is much more manageable because it's only governed by one of the 3 equations in this piecewise function. So the first integral from -1 to 0 is using the function x plus 1. The second integral is in the region of 0 to 2, which uses the function 2, and the third integral is in the region from 2 to 3, which uses the function 3 minus x. So for each of these, I find an antiderivative, and I evaluate it between the lower and upper bounds. I guess the other downside to this method is, while none of this calculation is terribly difficult, there is a lot of stuff to write out. And as you saw when I did the problem on the worksheet, it's actually pretty easy to make a small mistake when there's just so much arithmetic. What am I even doing now? I'm plugging in 2 minus 1/2 2 squared. And none of this is hard, but I do have to simplify all of this. Alright, 0, 0, positive 1/2, because it's negative, negative, plus 1, plus, well, this is just 4, and that's 0. And then I've got 9 minus 9 halves minus 3 times 2, which is 6, plus, because it's minus minus, plus 2. That's 1/2 of 4. So let's see, this is 3 halves plus 4 plus, oh boy, 9 minus 6 is 3 plus 2 is 5. I have 5 minus 9 halves, but 5 is 10 halves. So 10 halves minus 9 halves is 1/2. And this comes out to 3 halves plus 1/2, which is 2, plus 4, which is 6. Chat, help me out. Where's the mistake? Oh, okay. Okay. I can actually compare this, because I am computing these 3 parts of the integral separately. So I can see that the mistake is definitely in the first part. So let's just check that integral. X plus 1, the antiderivative is, oh, there we go. The antiderivative is not 1/2 x, it's 1/2 x squared. And how that's going to affect this is that I get negative 1/2 right here. Yeah, so it just changes. It changes this to a negative 1/2. So this is 1/2. Now it comes out to 5. Okay. So 2 different approaches, of course. We get the same answer with both methods once we fix the mistakes. Okay, I would also like to talk in more detail about the Riemann sums. On an exam, like our final exam, you would not be asked to do one of these crazy long calculations where you find the area of n rectangles and then take the limit as n goes to infinity. That is just too much for an exam. Too much for you to do, too much for us to grade. What you could see on an exam is you could be asked to compute a Riemann sum with like 6 rectangles or 4 rectangles, a small concrete number where you can actually plug in the x values and get the approximation using a particular small number of rectangles. So for that reason, I think it is worth looking at some examples with Riemann sums. And I think we should maybe even just look at the recitation project from last week, which is about Riemann sums. Again, this is a great review because it's focusing on the core concepts, which is the relationship between velocity and displacement, and this really important idea of using rectangles to approximate areas. So I'm going to work through this, and then I will show you something really cool with Riemann sums that I'm pretty sure you have not seen in class. Okay, so the girl is running at a velocity of 12 feet per second for 10 seconds, as shown in the velocity graph below. Yep, constant velocity of 12 feet per second. How far does she travel? Well, if she goes 12 feet per second for 10 seconds, distance is rate times time. Distance is rate times time. So I multiply the rate and the time, and the units don't cancel out quite like that. What I mean is that the seconds cancel with the seconds in the denominator here and leave us units of feet, which is correct. Checking the units is always a good way to make sure that we're doing reasonable computations. But I get 120 feet. And the key observation here is that the area of this rectangle is 120 feet. The area is it's exactly the same computation I did here. It's base times height. So 10 seconds times 12 feet per second. So the area between the velocity curve and the x-axis is the distance traveled. That's true if we're talking about a velocity that's only positive. If it's sometimes positive and sometimes negative, we have to think a little more carefully. That's why we usually find the net area. Oh, yep. That is what I was just talking about. Okay, so now she changes her velocity as she runs. Okay, cool. So how far does she travel? Well, in the first 4 seconds, she's going 12 feet per second for 4 seconds. So if I multiply those two together, rate times time, I get the distance she travels in the first 4 seconds. But then in the next 3 seconds, from time 4 to time 7, she travels at 10 feet per second. So rate times time, she'll go 10 times 3 feet. And in the third time interval here, from 7 seconds to 10 seconds, she's only going 6 feet per second. So she'll travel base times height, or rate times time, 6 times 3 feet. So all told, she runs 48 feet and another 30 feet and another 18 feet, which you've seen how I'm struggling at 9 p.m. with the arithmetic. Let's see if I can do this. 48 and 18 is 48, and 20 minus 2, which is 68 minus 2, which is 66. 66 plus 30 is 96 feet. If I'm wrong, please tell me. But once again, the distance she travels is the area underneath the graph. If we believed it, when the graph just makes one rectangle, well, we should believe that we can break the time interval down into these 3 time intervals where the velocity makes a rectangle, and then add the results together. And even if the velocity is not constant, this is the point. No matter what the velocity curve looks like, the distance traveled is going to be the area. Okay, cool. Now we're looking at an example where the speed is not constant. It's not made up of straight lines. It looks like it's part of a parabola, and that is in fact the case. Okay, so we don't have a formula for the area of a piece of a parabola like this. And so the strategy is to just approximate it using rectangles. Okay, so I need to do base times height to get the area of each of these rectangles. The base of each of these rectangles is 3. 0 to 3 is 3, 3 to 6 is 3, 6 to 9 is 3, 9 to 12 is 3. For the height, well, what's the height of this first rectangle? It's whatever the y value is for the parabola at t equals 3. So if I plug t into my equation, I get 3 squared over 12, which is 9 over 12, or 3/4. At time 6, the velocity is 6 squared over 12, which is 36 over 12, or 3. And I guess if I'm being careful, I should write the units. These are all velocities, so they're measured in feet per second. V of 9 is going to be (9 squared over 12), which is 81 over 12. Divide the top and bottom by 3, that's 27 over 4 feet per second. And the last one, at time 12, I get 12 squared over 12, which is 12 feet per second. So now I'm also supposed to estimate her distance traveled. This is an approximation. You can see it's fairly substantial over approximation because all of this area within the rectangles does not actually live underneath the parabola. But yeah, base times height for each rectangle. Base times height, base times height, base times height. And before I do all this arithmetic, let me just factor the 3 out from all of these terms. The 3 and the 12 make 15, the 3/4 and the 27/4 make 30/4. Thirty-fourths is 15 halves. 15 halves and 15 makes 45 halves. 45 halves times 3 is 135 halves. And that's feet. Okay. Whew. Now they want me to do the same thing again, but with 6 rectangles. I don't really actually want to do that calculation. We're going to get a better estimate, but it's still the same sort of, it's the same sort of thing. Let me just write out a couple of the terms. The first rectangle is going to have a width of 2 instead of 3 because I'm only going from 0 to 2 now. Or in other words, instead of splitting 12 up into 4 pieces, I'm splitting 12 up into 6 pieces. So the width is 2. The height is going to be 2 squared over 12. Plugging that 2 into the equation of the parabola. The second one, the rectangle is going to look like this. The width is still 2, and I'm plugging 4 in. So I get 4 squared over 12. I keep going. The last one is still has a width of 2, and the height is 12 squared over 12. Okay, so if I wrote out all 6 terms, I could simplify this. But I don't really want to. Now they've made this interesting. They want us to do this with 37 rectangles, and the point is we're not actually going to compute the area of all 37 rectangles. We just want to see the pattern. What's the width of each rectangle? Well, we're still going from 0 to 12. But now, instead of dividing that into 4 rectangles or 6 rectangles, we're dividing it into 37 rectangles. So the width of each rectangle is 12 times 37. 12 divided by 37. Now, the right-hand endpoints of the rectangles, the first one is at 12 37ths, because it starts at 0 and it goes 1 rectangle width to the right. The second rectangle, well, we start at 0 and we go 2 rectangle widths to the right. So that x value is 2. 2 times 12 37ths. And the third one is 3 rectangle widths to the right of 0. And so on. The last one is 36 rectangle widths to the right of 0. And the very last one is 37 rectangle widths to the right of 0. And you'll notice that 37 times 12 37th is 12. And yeah, of course, the last rectangle is supposed to end at 12. What are the heights? Well, these are the x values. And to get the y values, I just plug the x values into the formula for velocity. And that formula is t squared over 12. I'll write that as 1/12 times t squared. And the last one is 1/12 times 37 times 12 over 37 squared. The areas of the rectangles. Well, the area of the first rectangle is its base, which is 12 37ths, times the height, which is this thing. And the area of the second rectangle is its base, which is still 12 37ths, times the height, which is all of this. And we could keep going all the way up to the last one, which is 12 37ths times the height. Starting to get a little bit messy, but the sum of all the areas, well, we're just adding all these together. I'm not going to copy that out again. Okay. I think it's valuable to do this with 37 because, our brains like specific numbers. But now that we've done that, instead of 37, we're just going to basically replace all the 37s with n's. So the width of each rectangle is 12 now, not divided by 4, not divided by 6, not divided by 37, but divided by n. The right-hand endpoints, well, the first one is going to be at 12 over n instead of 12 over 37. It's 1 rectangle width to the right of 0. The second x value is at 2 rectangle widths to the right of 0. And then 3 rectangle widths to the right of 0. And so on, all the way up to, I wrote 36 and 37 here. I'm still stuck thinking of 37 rectangles. There are n rectangles now. So the last x value is n rectangle widths to the right of 0. But of course, n times 12 over n is 12. And we're always supposed to end up with 12 as the final x coordinate. Well, if the last one is n, the one before that must be n minus 1. The heights of the rectangles are the x values squared divided by 12. I am just using the x value and plugging that in as the t value. Every time I say x value, I really mean t value. All right, 1/12 times the t value squared. 1/12 times the t value squared. The area of the rectangle is the base times the height. Base times height. Base times height. The sum of all the areas is all these things added together. It'll be easier to write this in sigma notation. And I guess I should actually write this out. It'll help me to write the sigma notation if I have this written out for real. 12 over n times 1/12 12 over n squared. 12 over n, that's the base, times the height, which is 1/12, to 12 over n squared. And so on all the way up to 12 over n times 1/12 n 12 over n squared. Okay, so we have a whole bunch of rectangles. How many do we have? We have n. So I'm going to write this as a sum from I equals 1 to n. I is keeping track of which rectangle I'm looking at. I equals 1 is the first rectangle, I equals 2 is the second rectangle, I equals n is the last rectangle. So in each term here I have a 12 over n times 1/12 and then something times 12 over n squared. Oop, 12 over n, and the something is also being squared. So if you look at all these terms here, every single one looks like this. The only difference is that number being multiplied with the 12 over n, and that's I. In the first term, I equals 1. So if I replace that with a 1, I get this. In the second term, I equals 2, so if I replace the I with a 2, I get this. In the third term, I equals 3. If I replace I with a 3, I get the third term. The last term is when I equals n. If I replace the I with an n, I get this. Would it behoove of us to expect a small Riemann sum into summation form question for the final? You mean something like writing this as with summation notation? Or so I mean, I've seen a variety of questions on finals in the past. I've seen questions kind of like this one or this one where you're not the 37, but the 6 or the 4, where you were asked to actually compute the value of the Riemann sum. And usually we don't really care if you simplify it to this. We just want to see that you can write out what the Riemann sum is. So usually this is a perfectly acceptable answer. And yeah, if they don't tell you to simplify it, You've seen how many arithmetic mistakes I've made tonight. Don't even bother simplifying it down to a single number. Another kind of question that you could see on a final exam is to write out a Riemann sum like this that evaluates a function, or evaluates a definite integral. So if we give you the integral of 1/12 t squared from 0 to 12, we might ask you to write out this expression. We would certainly not ask you to evaluate this expression as a limit of Riemann sums. It could go the other way too. We could give you this expression and ask you, what definite integral does it represent? So we give you this, and you need to recognize that this is the definite integral that it represents. I know there are questions of that form on some of the practice exams, so that'd be a good thing to look at. Okay, cool. Yeah, so keep the questions coming if you have any. This activity is going to ask us to actually compute this Riemann sum, though. So, let me copy this. Now, this Riemann sum is not quite so bad. There are definitely much worse ones. And the reason that it's not so bad is, first of all, because the function only has one term. It's just 1/12 t squared. But another thing that's really nice is that it starts at 0. When it doesn't start at 0, you have to do some foiling. So it just gets a little messier. So the thing to notice, I guess, first of all, is these 12s cancel. And so before I even do anything with the sum, let me just simplify what's inside the sum. I have a 1 over n. I have an I squared, because when you have two things multiplied together, being squared, you square both of them. So it's an I squared and then a 12 squared, which is 144 over n squared. So if I group together the stuff that doesn't have an I and the stuff that does have an I, I've got the I squared, and then 1 over n times 144 over n squared is 144 over n cubed. And I wanted to group that together because the 144 over n cubed comes outside of the integral. The sum. The point is that this sum thinks that I is the variable. Anything that's not an I, even if we view it as a variable, if it's not an I, the sigma doesn't think it's a variable, so it can come outside of the sigma. The I's are stuck inside the sigma. And it's the same thing as with derivatives. When you differentiate with respect to x, anything that's not an x is a constant as far as the derivative is concerned, so it can come outside of the derivative. Same idea. And just to clarify why we have now something of the form of stuff times 1 plus 4 plus 9 and so on, I have 144 over n cubed. And what does the sum mean? It means, well, replace that with a 1, replace it with a 2, replace it with a 3, and so on. 1 squared plus 2 squared plus 3 squared, all the way up to, what's the last thing we replace it with? It's n. And that is exactly what we were trying to write this as. Is the area under the curve considered a derivative? What is the relationship between area under the curve and derivatives? Yeah, so these are very much inverse relationships. You should think of these as inverse processes, sort of similar to how the natural log is the inverse function of the exponential function. These are not functions, but they're sort of inverse processes. In terms of position and velocity, velocity is the derivative of position, but position is an antiderivative of velocity. So I find the slope of the tangent line, I take the derivative to go from position to velocity, I look at the area underneath the curve to go from a velocity graph back to finding displacement, which is how much my position changes. So that's the relationship between derivatives and the area under the curve. They're opposite processes. I hope I answered your question. If not, let me know if there's something I can say more about. So we are almost done here. We're just going to use this formula, and maybe at the end of the stream I will show you where this formula comes from, because it's not really important for you to know, but I think it's really cool. So I want to make it available to you, but I'll put that off until the end, so you can just tune out if you are not interested in knowing that. But I'm using this formula that this sum of the first n perfect squares is n times n plus 1 times 2n plus 1 over 6. And that's going to simplify a little bit, because the n in the numerator cancels with one of the n's down here. It leaves us with an n squared. And I also have the 6 in the denominator. 144 is divisible by 6. 144 is 12 times 12, which is 12 times 2 times 6. So if I cancel a 6, that leaves me with a 12 and a 2, which is 24. And in order to take this limit, I'm going to simplify this even more. I'm going to FOIL out the numerator. That's n times 2n plus n plus n plus 2n, which is 3n, and then plus 1. And if I distribute the 24 over n squared, I'm going to get 48 plus 72 over n plus 24 over n squared. So, sorry about that. Let's, okay. The screen is back. Oh, sorry, I went a little bit off the screen here when I was writing this. I have to remember that I don't quite have the full width of my iPad being shown. So something to point out, if I took this formula and if I substituted in n equals 4, I should get 135 over 2. Assuming that I didn't make any arithmetic mistakes here, which maybe is a dubious assumption. If I plugged in n equals 6 in that formula, I would get whatever this comes out to. And if I plugged in n equals 37 in that formula, I would get whatever this sum comes out to. And that's pretty cool, because this sum involves so much arithmetic that I didn't even bother to write out all the terms, let alone try to evaluate that. But plugging in 37 wouldn't be pretty hard here. I would just plug that in, and it's just 3 fractions added together. I'd probably use a calculator if I wanted the actual value, but it's only 3 fractions being added together. But the point is that the more and more rectangles we use, the better of an approximation we get. And if we want the best approximation, not even an approximation, but the actual area underneath the curve, I just take the limit as n goes to infinity, which means using more and more and more rectangles. And this is the easiest limit that we maybe take in the whole course, unless there's like a direct substitution limit. But as n gets really large, you're dividing 72 by huge and huger numbers. You're dividing 24 by really big numbers because you're squaring them. Both of these terms go to 0. You're just left with 48. Yeah, and we should be proud of ourselves. We found the area inside a region with a curved edge. That's not something you do every day. It's not even something I do every day. All right, so I want to show you another example of this sort of thing. Finding an area, which means evaluating a definite integral using a limit of Riemann sums. I want to show you an example that in the 5 semesters I've been teaching Calc 1, I've never shown this example in class. I would love to, but I don't have time, and it's a little more advanced. The cool thing about it is that I'm going to get to show you something that you'll use in Calc 2. Oh, I just realized, wait, are you not quite seeing, oh, you're not even quite seeing the top of my screen. Okay. But yeah, I want to give you a little preview of some cool stuff from Calc 2. We're going to evaluate the integral from 0 to 1 of e to the x. Using a limit of Riemann sums. Of course, we know what the answer is using the fundamental theorem of calculus. It's pretty quick. I find an antiderivative, which is just e to the x. I plug in 1, I plug in 0, I subtract. E to the 1 minus e to the 0, which is e minus 1. So we should get e minus 1. But if we didn't know the fundamental theorem of calculus, how would we come up with that? The exponential function looks something like this. At x equals 0, the value is 1, and at x equals 1, the value is e. And we're going to be dividing this up into a bunch of little rectangles. I will continue to use the right Riemann sums, meaning I'm using the right endpoints to set the heights of the rectangles. So let's actually just call the Riemann sum, maybe we'll call it R sub n, because it's a right Riemann sum, and I'm using n rectangles. Hello, Horse. Thanks for joining us, and yeah, hope to see you next time. So the Riemann sum, I'm adding together the areas of a bunch of rectangles. Oh. I think something weird just happened with the setup here. Okay, that looks a little more reasonable. Okay, so I have some rectangles. I'm going to use n rectangles. So once again, I'm summing from I equals 1 to n, and I'm doing base times height. 1 over n is the base of each rectangle, because I'm going from 0 to 1. The total width of all the rectangles is 1, and there are n rectangles, so I'm dividing that width of 1 into n different pieces. And then the height of the rectangle is e to whatever the x value is. And the x value of the ith rectangle, let's look at the x value of the third rectangle. So here's that x value. It's 3 times 1 over n. How do I know that? Well, I started at 0, and then I hopped 3 rectangle widths over to the right. So I add 3 multiples of 1 over n to my starting x value of 0. And then if I look at the y value, well, the graph is y equals e to the x, so the y value is e to the 3 times 1 over n. Okay, so that 3 is because I'm looking at the third rectangle, but in general, it's going to be I. So this is my right Riemann sum. It's the sum of 1 over n times e to the I times 3 over n. That 1 over n can come outside of the sum because it doesn't have an I in it. And then this e to the I times 3 over n, I'm going to write this as e to the 3 over n times I, or to the I. I'm just using rules of exponents. The reason is that now I've got just a constant raised to the I. And by constant, I mean not depending on I. How do I evaluate this sum? So we've gotten to the point in evaluating this Riemann sum where we need to use a formula that just tells me how to add up all of these terms. But I want to show you where that formula comes from, because it's really cool, and you will see this again in Calc 2. This is something called a geometric series, where what we're trying to do is we're trying to add something. I'm going to refer to the first term as A, and then each term beyond that is the same multiple of the previous term. From each term going to the next, I multiply by the same thing. I'm calling that thing here R. R for ratio. And that's what we have happening here. When you raise e to the 3 over n to the ith power, every time we move on to the next rectangle, that I is going up by 1, which means we're multiplying by one more copy of e to the 3 over n. So the last term here is a times r to the n minus 1. Because if I have n terms here, then to get from the first to the last, I'm taking n minus 1 steps. Okay, we want to evaluate this. The really neat trick here is if I call this s, as in sum, I'm going to look at r times s. If I multiply this whole thing by r, and let me actually even put the r on the right to make it a little more clear. A times r is r, ar times r is ar squared times r is ar cubed, and then I get an ar to the 4th, and so on, all the way up until the last one, which is ar to the n minus 1 times r, or ar to the n. Now the really interesting thing here is that these two terms are almost the same. They're almost the same. So what's the difference between them? If I look at SR, it is almost the same as what S is, except SR starts with AR. It doesn't have an A. It doesn't have that A term. So I should take this thing and subtract off the A. And then what do I also need to do? I need to add on an AR to the N. If I take S and cross out the first term and then add in that last term, I get SR. And here's the cool part. Now I can rearrange this. If I subtract over S and factor out the S, I get the sum. So there we go. This is a formula that tells me what that sum is. Okay, so the sum, well, in this case, A, the initial term in the sum, that happens when I equals 1. So it's e to the 3 over n to the 1, or just e to the 3 over n. And what's r? It's the thing that I'm multiplying by every time I move to the next term, which happens when I goes up by 1. It means we're multiplying by one more e to the 3 over n. So r is also e to the 3 over n. So if I use this formula, I get a r to the n minus a over r minus 1. Let me clean that up just a little bit. I see that I can pull out an e to the 3 over n on the top, and then left with, well, when I raise e to the 3 over n to the n, I get e cubed. Sorry, where's this 3 coming from? Oh my gosh. Sorry, that 3 was supposed to be a 1 the entire time. Alright, apologies for that. E to the 1 over n to the n is just e to the 1. Because I multiply the exponents. So I factored out the e to the 1 over n, and that leaves me with e minus 1. And in the denominator I have e to the 1 over n minus 1. Now that e minus 1 is a constant. So if I pull the constant out and group everything else together, here's my expression. And now we'll actually get to review some calc 1. This is not just calc 2 stuff that you don't need to care about. I need to take the limit of this as n goes to infinity. Limit as n goes to infinity. The first thing I notice is that the e minus 1 is a constant, so it comes outside of the limit. So where am I going with this? What happens as n goes to infinity? 1 over n is going to 0, so e to the 1 over n is approaching e to the 0, which is 1. And my denominator, oh, the denominator is weird. The n going to infinity, but e to the 1 over n is going to 1. So when I subtract 1, that's approaching 0. So I've got an infinity times 0 in the denominator. This is feeling L'Hopital-ish. So what if I move that n in the numerator, or the n in the denominator, up to the numerator as a 1 over n? Well, now in the denominator, well, the numerator is going to 0, because this is going to 1, but I'm dividing by an n, so that's going to 0. And we said already that this thing goes to 0, so this is actually a 0 over 0 indeterminate form. So I can use L'Hopital's rule. Okay. Again, you might think it's silly to do all this. Look ahead to Calc 2. I know you're busy enough worrying about all of your responsibilities for this semester, but we are going to get to review some good stuff like L'Hopital's rule, and then taking this derivative. Well, I need to use the product rule up here, so I'm going to differentiate the 1 over n to get minus 1 over n squared, and I'll leave the e to the 1 over n alone, and then I'll leave the 1 over n alone, and I'll differentiate e to the 1 over n, which by the chain rule gives me e to the 1 over n times the derivative of the 1 over n. Oh, sorry, that's a plus. The product rule has a plus sign. In the numerator, or in the denominator, I'm differentiating e to the 1 over n. I just did that. I know that I get 1 over n times e to the 1 over n. Oh, sorry. Just e to the 1 over n times the derivative of 1 over n. There we go. So we had to use the product rule and the chain rule. Now the nice thing is that I see a minus 1 over n in both terms on the top and in the bottom. Oh, and I also see an e to the 1 over n in both terms in the top, and I see it again in the bottom. So L'Hopital's rule is really helping us out here. What's left in the top? 1 plus 1 over n. And in the denominator, there's nothing left, so we're dividing by 1. Okay, so all we have left is 1 plus 1 over n. And as n goes to infinity, that second term, the 1 over n, goes to 0. So we get e minus 1 times 1, which is e minus 1. And that is also what we would have gotten using the fundamental theorem of calculus. But I think it's really cool that you can come up with this answer even without using the fundamental theorem of calculus. All right, what else should we talk about? I asked my students if there are any topics they wanted me to review, and they mentioned optimization and linearization. So maybe let's look at optimization. And I guess, yeah, now we're getting into the part of the review session, which is actually a good old-fashioned review session looking at topics from earlier in the course. Okay, here's a cool problem. A movie screen on a wall is 20 feet high and 10 feet above the floor. And what I want to know is at what distance should you sit from the screen to maximize your viewing angle. Now, students in my class know that the first thing I always want to do with a word problem of any kind, really, whether it's related rates or optimization, is to draw a picture. So let's draw the wall, then the ground, and let's draw the screen. And then let's draw the person down here. You know, they didn't tell us like how high your head is above the ground, so we're not worrying about that. For the sake of simplicity, we'll imagine that you were just at the ground. The screen is already 10 feet up in the air. It's maybe in the real world we wouldn't totally neglect this, but for the sake of simplicity, we're going to ignore it. So that's 10 feet. And this is 20 feet. And we're trying to maximize the viewing angle, which is this angle theta, made by the lines from your eyes to the bottom and the top of the screen. So so do we even believe that there should be a maximum angle? Well, I think so, yeah, because if you sit right below the screen, your viewing angle is tiny. I mean, if you're right up against the wall, your viewing angle is literally 0. Whereas if you're very far away, it's trying to go so far it won't even let me draw a line. But if you're really far away, you can see the viewing angle is really small, and the farther away you get, the smaller that angle gets. But somewhere in the middle, there should be a sweet spot where that angle is maximized. Okay, so just drawing a picture already makes it a lot easier for me to think about this problem. Okay, so in an optimization problem, there's something you can control directly, and something that changes as a result of that. The thing that's changing as a result is this viewing angle. That's what we want to maximize. But what's the thing that you can control? It's how far away that you sit from the wall. So let's make up a variable for that. Let's call that x. So I guess maybe not even the goal, but the strategy. And even though this problem, it might be a little bit complicated, it's unfamiliar, you might never have seen a problem like this before, it's an optimization problem. The strategy is always the same. You want to write a function, or let's say express the viewing angle. You always want to express the thing that you're trying to maximize as a function of the distance x from the screen. And x here is the independent variable. It's the thing you can control. We're always trying to write down a function that we can maximize using calculus. Once we have a function, that's kind of the hard part. That's specific to each different problem. We have to reason about this scenario and write down a function. Then we optimize using calculus. Find the critical numbers. Think about if there are endpoints. First derivative test, second derivative test. Okay, so can I write down an equation involving theta and x? Trying to find the angle between these two lines. Whenever I'm trying to find a quantity between two other quantities, I can always think of that as the difference in two quantities. And what I mean is, if I measure this angle here and call it theta 2, or theta 1, and I measure the angle to the top of the screen and call it theta 1, sorry, numbers. Theta 1 is the angle from the ground up to the bottom of the screen. Theta 2 is the angle from the ground up to the top of the screen. Theta is the difference between these two angles. It's theta 2 minus theta 1, because theta 2 is the bigger one. So yeah, my thought here is I'm trying to measure a quantity that's between two other things. So I should look at those two things independently and subtract them. Okay. Now I feel good because I see this triangle here. I see that we have an angle labeled, and I see that two of the sides are labeled. So, trig function. What do I know? I know that the tangent of theta 1 is 10 over x. Opposite over adjacent is the tangent of the angle. And then I see this triangle here. Opposite over adjacent, well, that's 10 plus 20, which is 30. So 30 over x is the tangent of theta 2. But I'm trying to find theta, so I want theta 2 and theta 1 themselves. How do I get the angles if I know the tangents? Well, I take the inverse tangent. Theta 1 is the inverse tangent of 10 over x. Theta 2 is the inverse tangent of 30 over x. So theta is theta 2 minus theta 1, which is inverse tangent of 30 over x minus inverse tangent of 10 over x. There it is. There's my function. I have expressed the viewing angle as a function of how far away I'm sitting from the screen. So now that I have a function to maximize, we're gonna start by finding the critical numbers. So I'll need to take the derivative of both sides. Let's see, the derivative of arctangent. Well, the derivative of just plain arctangent of x is 1 over 1 plus x squared. So the derivative of arctangent of 30 over x is 1 plus 1 over 30 over x squared. But the chain rule says I also need to multiply by the derivative of 30 over x, which is minus 30 over x squared. And then the derivative of arctangent of 10 over x is 1 over 1 plus 10 over x squared times minus 10 over x squared. All right, let's simplify this a little bit. I'm just going to expand out that 30 over x squared. That's 900 over x squared. And this 10 over x squared is 100 over x squared. And then I'll multiply these two fractions together. I multiply the numerators, and I multiply the denominators. Same thing over here, multiply the numerators, multiply the denominators. Okay, and that doesn't look so bad. Okay. Now, critical numbers happen when the derivative is 0 or undefined. Is this derivative ever undefined? Well, the only way that would really happen is if the denominator was 0, but actually it never can be 0. I guess before the simplification, the derivative could be 0. But we don't consider an endpoint to be a critical number. And the domain of my function really is from 0 to infinity. The distance from the wall can be as small as 0 and as large as you want. Okay, so mainly I'm looking for places where the derivative is equal to 0. This is a strange equation. I don't know that I've seen an equation quite like this before, but let's just apply our usual strategies. I think it might be helpful if we brought the 30 over to the left side by adding 30 over x squared plus 900 to both sides. I also think it's usually helpful when you don't have a variable in the denominator. Variables and denominators are complicated. So I'm going to take the reciprocal of both sides of the equation. I can do that as long as I'm doing the same thing to both sides of the equation. I feel much better about this equation, because now there are only variables in the numerator. And now I think I can easily get rid of these fractions by multiplying both sides by 30. On the left side, that completely cancels out my fraction. On the right side, it cancels out my fraction and leaves me with an extra factor of 3. Because 30 over 10 is 3. If I distribute the 3, I get this. Let's gather like terms. If I subtract 300 from both sides, I end up with 600 over here. If I subtract x squared from both sides, I end up with 2x squared over there. So x squared is 300, and that means x is the square root of 300. That does actually simplify a little bit. It's 10 times the square root of 3. Is this a reasonable amount? Square root of 3 is about 1.7. Multiply that by 10, you get about 17. So 17 feet away from the screen. Seems reasonable. It's probably somewhere around here. I could believe that. I could definitely believe that. Now, the question as written was just asking at what distance we should sit. So this x value is what we were looking for. I'm a little curious whether we can actually evaluate evaluate the viewing angle. Theta was arctangent of 30 over x. Minus the arctangent of 10 over x. Oh, this is beautiful. This simplifies so nicely. Wow. So 30 over 10 gives 3, so I just have 3 root 3 in the first arctangent. And then in the second arctangent, the 10s cancel. But 3 over root 3 is the same as just root 3. And it just so happens that root 3 and 1 over root 3 are two of the very few things that I know the arctangent of. Root 3 is the arctangent of pi over 3. 1 over root 3 is the arctangent of pi over 6. These are just two of the 3 angles between 0 and 90 that we know. And we know the tangents, or all the trig functions for. They're two of the 3 special angles in the first quadrant. This is pi over 6, or 30 degrees. So apparently 30 degrees is the biggest viewing angle that you can get looking at a screen which is twice as tall as the bottom is above the ground. Now, whoever wrote this problem, it wasn't me, I found this problem somewhere, but whoever wrote this problem, I guess, just thought this out carefully. They chose these numbers so that the algebra would work out nicely. But that's really cool that it comes out to just a clean 30 degrees. Okay, now if you're doing an optimization problem, we should actually make sure that our critical number is a maximum, and an absolute maximum, not just a critical number. Some critical numbers are local minima, or absolute minima, or stationary points, neither minima nor maxima. So how do we actually know that x equals 10 root 3? And I should use units. Always include units. Always include units. This is in feet. Always include units. How do we know that this is an absolute maximum? Well, the way that you go about optimizing a function depends on the domain of the function. If the domain is a closed interval, that's the ideal scenario, because then you know that, first of all, that there is an absolute maximum and an absolute minimum. We know that by the extreme value theorem. And if the function is continuous, and the domain is a closed interval. But we also know that the absolute maximum and minimum can only happen at a critical number or at an endpoint. So we just evaluate the function at the critical number, well, all the critical numbers, and the endpoints, and we see what's the biggest and what's the smallest. if the domain is not a closed interval, we have to think a little more carefully. It's not as algorithmic of a procedure to determine whether we have an absolute minimum or a maximum. So what do we have here? The domain of our function, which represents the viewing angle as a function of x, the distance that you sit from the screen. The domain is, well, what's the smallest that x could be? I'd say 0. Could you really sit right at the screen? Probably not. I don't think, yeah, you can shove your head up very close to the wall, but your head cannot be literally at the same place as the wall. So I would probably not include 0 in the domain. And also, if you look at our function, if you plug in x here, you get division by 0. So this function, this equation doesn't really even make sense at x equals 0. Now, we should say the domain does not include 0. There is a case to be made that you could include 0 in the domain. Why is that? Well, if you look at this function, and this is not, a thought that I would expect anyone to have under the time pressure and the stress of taking an exam. But I think it's something that I want to point out. If you look at this function, as it approaches 0, even though the equation I wrote down here is not defined at 0, because you divide by 0, the function is approaching 0. And the fact that you can't plug in 0 is kind of just it's some sort of weirdness of the way that I wrote down these equations, but it seems intuitively clear to me that at the actual point here on the wall, the viewing angle should be 0. Because theta 1 is going to be exactly 90 degrees, and theta 2 is going to be exactly 90 degrees. You have to look straight up to both the bottom and the top of the screen. I guess the reason that our function doesn't look like it should be defined at x equals 0 is really just that when you get right up here, there's no triangle. There's no triangle anymore. The triangle collapses into a line segment. So trying to do trigonometry to a triangle that doesn't exist leads to some weirdness. Anyway. But is there a limit to how big x could be? No, I don't think so. So the domain should be 0 to infinity. That's not a closed interval. So we need to think a little more carefully about this. Now, the good news here is that there is only one critical number. And something that you've learned is that if there's only one critical number, and if it's a local minimum, it's also an absolute minimum. If it's a local maximum, it's also an absolute maximum. So I really only need to show that 10 root 3 is an absolute, or is a local minimum. Sorry, local maximum. And I've got two tools for doing that. I have the first derivative test and the second derivative test. I think I want to use the first derivative test. So I'm going to make a sign chart for the derivative. So 10 root 3 is my critical number. So I just need to plug in something less than 10 root 3 and something bigger than 10 root 3 and see if I get a positive number or a negative number. And where is my derivative? It's up here. I simplified it down to this. What would be good numbers to plug in? I see lots of 10s and some 30s. Like, here's a 30. And 900 is 30 squared. So I kind of want to plug in 10 and 30. And 10 is, in fact, less than 10 root 3. Because you have to multiply by root 3 to get from 10 up to 10 root 3. And then if I multiply this by root 3, I get 30. So 30 is bigger than that. So if I plug in theta prime of 10, let me copy this expression. This was theta prime. Oh no, it's not letting me paste. Okay. Oh, maybe I just need to have something different selected. No. Sometimes this happens to me. I don't know how to paste things. Okay. I can remember what this was. Minus 30 over x squared plus 900. Plus 10 over x squared plus 100. If I want to add these fractions, how do I add fractions? I find a common denominator. I'm going to multiply the numerator and denominator of the second fraction by 5. When I add these together, I get 20 over 1,000, which is 1 over 50, but the important point is that it's positive. And now I'm going to plug in 30. The best I can do here for a common denominator, I guess these fractions actually simplify. But here the best I can do for a common denominator is 300, so that's going to be 3 over 300. And this is going to be minus 5 over 300. This comes out to negative 2 over 300, which is minus 1 over 150, but really the important point is simply that it's negative. Whew! Okay, so our function, the derivative goes from positive to negative. That means the function goes from having a positive slope to having a negative slope. So it goes from increasing to decreasing. That's a local maximum. So by the first derivative test, theta of x has a local maximum at x equals 10 root 3 feet. Since this is the only critical number, it's also an absolute maximum. So we finished the problem. Now this is a harder than average optimization problem. This is not the kind of thing that we would expect you to do on an exam. But I hope that, even if you don't feel like that you would have been able to do this flawlessly under the time pressure of an exam, I hope every individual step made sense and you feel like you could come up with these ideas by following the general strategy for an optimization problem. Draw a picture. Use what you know, looking at that picture, to find an equation modeling the thing you're trying to optimize in terms of the thing that you have control over. Then use calculus to optimize. That means find the critical number, set the derivative equal to 0, solve, and then think about what the domain is and how we can actually verify whether we have absolute minima or maxima. In this case, I used the first derivative test and the fact that there's only one critical number. Alright. It's getting late, and I see I only have one devoted viewer left. Thank you for sticking with me. As promised, I do want to show you, just for fun, how we come up with those summation formulas. This is purely for fun. If you don't have the mental energy or the interest to stick around, thanks for joining me. I'll see you in the next review session. But for anyone who's curious, we're going to deduce the summation formula, the sum of the first n perfect squares, and this is supposed to come out to n plus 1, 2n plus 1 over 6. And the magic idea that makes this work, and I don't think I would ever have come up with this on my own, but the idea is to consider the expression the sum from I equals 1 to n of I plus 1 cubed minus the sum from I equals 1 to n of I cubed. Okay, how do you come up with that? Someone had a flash of inspiration. And no, this is not a typo. You might be thinking we're trying to do the sum of I squared. Why do I have cubed here? That actually is correct, I think. Again, it's late and I'm tired. But I think this is the thing that we want to consider. And I'm going to simplify this two different ways. So the first way is sort of the more straightforward way, which is that when I have two sums, just like when I have two limits or two derivatives or two integrals, I can combine them together. Now, what is I plus 1 cubed? Well, if you factor that out, it's I cubed plus 3i squared plus 3i plus 1. But then you also have this minus I cubed. And the nice thing about that is the I cubes cancel out. So I'm left with 3i squared plus 3i plus 1. And I can simplify this First, by breaking this into three different sums, the sum of 3i squared plus the sum of 3i plus the sum of 1. That first sum, I'm going to pull out the constant multiple of 3, and what am I left with? It's the sum of I squared. This is the thing that I'm trying to solve for. And here, I pull out the 3, and I'm left with the sum of I, and here I have just the sum of 1. So this first sum, I don't know. That's the thing that we're trying to deduce. But I do have a formula for the sum of I. Yeah, we have to argue about why that's true. But that one's a little easier to show. And that's something that I talked about in class, in my section of calculus. And the sum of n ones is n. Okay. But there's a totally different way to simplify this, and it's really cool. So what does this mean? The first sum is 2 cubed plus 3 cubed plus 4 cubed, and so on, all the way up to n cubed, and the last term is n plus 1 cubed. The second sum here is 1 cubed plus 2 cubed plus 3 cubed, and so on, all the way up to n cubed. Now, when I subtract these, almost everything cancels out because all of these terms are being subtracted. Right? So the 2 cubed cancels, and the 3 cubed cancels, and the 4 cubed cancels. I didn't write the 4, but there's a 4 cubed in there. And the n cubed cancels. All that's left is this n plus 1 cubed. That doesn't cancel because there's no n plus 1 cubed in the second term. And then this 1 cubed, that doesn't cancel with anything because the first sum started at 2. And if I expand this out, I get a little more cancellation even. That equals n cubed plus 3n squared plus 3n. So now I have these two expressions, which both came from simplifying this same mysterious original expression. So these are equal. So if I set 3 times this sum plus 3n n plus 1 over 2 plus n equal to this n cubed plus 3n squared plus 3n, I can solve for this. Before I subtract anything over, I'm going to expand this out. This is 3 halves n squared plus 3 halves n. And now I'm going to subtract all this over. N cubed plus 3n squared plus 3n minus 3 halves n squared. I'm subtracting this over, and then I'm going to combine these to make 5 halves n and subtract that over. But now I can clean up the right side. 3n squared minus 3 halves n squared is just a plus 3 halves n squared. And then 3n minus 5 halves n is a plus 1 half n. I'm going to multiply both sides by 2 to get rid of the fractions. We're almost there. The right side, factors. The first thing you notice is that there's a common factor of n. Once you pull that out, you just have a quadratic left. And you know how to factor a quadratic. It turns out to be n plus 1, 2n plus 1. And to finish this off, I divide both sides by 6. There we go. That's how I come up with the formula. I'm absolutely not going to work this out right now. But this method continues. If you want a formula for the sum of I cubed, you can look at the sum of I plus 1 to the fourth minus I to the fourth, and simplify that the two different ways. And on your way, you will need to have handy the formulas for the sum of I and the sum of I squared and the sum of 1. But you'll get a formula for the sum of I cubed. And then make these 5s, and you'll get a formula for the sum of I to the fourth, and so on. And you can keep getting all the formulas. Anyway, if you were still watching, thank you for sticking around for so long. I hope this has been helpful. If you have suggestions for things you'd like to see in future review sessions, send me an email. I will try to get this posted. But if you were watching this right now, unless you're the one person who's watching live, then I guess that means that I have succeeded in getting it posted. Or you're watching